All right, so come over here, and they talk about a strategy for finding limits, right? And they give us three different options. Number one, learn to recognize which limits can be evaluated by direct substitution. In other words, if we can plug the number in, plug the number in. Because that is easiest. And we like easy. So if we can do it, do it. 2. Bless you. When the limit of f of x as x approaches c cannot be evaluated by direct substitution, why would it not be able to be evaluated by direct substitution?
Denominator 0.
Denominator is 0, most likely. Try to find a function g that agrees with f for all x other than x equals c. Does that make any sense, or is that weird speak? Okay, that's what I thought. Remember yesterday, the last one we did, where we canceled out, we factored, and then we canceled the numerator and denominator? Yeah. And then we were able to plug it in? That's what they mean. So basically, if we have something like f of x equals x squared minus 9 over x minus 3, let's say. And let's do this instead. Let's go limit as x approaches 3 of this. How would this work? Well or poorly? Poorly, because 3 would make the denominator 0. So no dice there. But remember what we did yesterday. So this is saying try to find a function, g, that agrees with f for everything except for that 3. In other words, factor the top. Cancel what we can. And so now let's try to find the limit as x approaches 3 of x plus 3. That's easy, right? We're happy with that. So that's what this is saying. Find a function g, so this would be our function g, that agrees with f. In other words, this, is it fair to say that this is the same as this? Except at one point. At 3. Except at 3. Because at 3, this is undefined, and this is 6. So that's what they're saying here. Find a function g that agrees with f for all x's other than x equals c. Does that make a little more sense what they're saying here? Okay. So this function and this function are exactly the same, except that when x is 3. Choose g such that the limit of g of x can be evaluated by direct substitution. And then apply. So that's what they're saying in part 2. They do what we just did. And we'll see a couple of other ways to do that also as we go on. Number 3, use a graph or a table to reinforce your conclusion. Okay. So we certainly could plug this into our calculator, check out the table or the graph, and see that it goes to 6 there. Reasonable? So that's, when applying the strategy for finding a limit, remember that some functions do not have a limit. Some functions don't have a limit. We remember that? When would it not have a limit? When they're approaching a different number. So one's going that way and one's going that way, and the limit at this number doesn't exist because one's way up here and one's way down here. Good. What's another one? Another reason that a limit would not exist? Oscillating behavior, that's where I was going with that. Yeah. The oscillating behavior is also part of that. So basically, different left and right behavior, oscillating behavior, and there's actually one more that we haven't talked about yet, and that is, they call it unbounded behavior. So if the graph is going to infinity, we don't say that the limit is infinity. We won't say that at this point. We would say it doesn't have a limit. If it's it's going to negative infinity. We would say it doesn't have a limit. Does that make sense? Okay. All right. Where are we? So we are going to talk about a couple of ways to get these limits. Remember we said if, to try to get functions that are equal to those functions except at a point. Okay. So the next theorem concerns the limit of a function that is squeezed between two other functions, hence the name of the theorem, which is called the squeeze theorem. I love the squeeze theorem. Each of which has the same limit at a given x value as shown in figure 1.20. Boop. There we go. So basically, it's between, f is between g and h. And so g and h are going to have this limit. So f is going to be the same. So we'll talk about that here. If h of x is less than f of x is less than g of x for all x in an open interval containing c, except possibly at c itself, and if the limit of h of x is L, and the limit of g of x is L, then the limit of f of x is also L. The squeeze theorem doesn't come up that often. I just think it's cool and I like the name. But I do not see the squeeze theorem very often. Okay. You can see the usefulness of the squeeze theorem, also called the sandwich theorem or the pinching theorem. The proof of theorem 1.9. So that's kind of here. But more importantly are these three special limits. You want these three special limits. Okay. Up at the top of theorem 1.9. You want these limits. The limit as x approaches 0 of sine of x over x equals 1. The reason you want to know that is because logically, I'm not sure it really makes sense. It doesn't click to me at any point that sine of x over x would be 1. So the second one is the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. That's another one. That's like the last one. And the third is the limit as x approaches 0 of 1 plus x to the 1 over x power equals e. Those, more than anything, are just remember, memorize them. Okay? Okay, we're all right with those three? We just got to know them. All right, so let's take a look how some of this stuff is going to apply. Find the limit as x approaches 0 of tan of x over x. Yep. Who's out? So direct substitution work okay here? No, why not? Denominator 0. So that's no good. So what we can do then, direct substitution said the indeterminate form. Wow, that's the first time I've ever seen that we've seen that word. We talked about it on August 6th a year ago. We talked about the word indeterminate, but we never saw it until now. Yay. Okay. So basically, what they're going to do is they're going to say, all right, let's take tangent of x and write it as sine over cosine. and let's manipulate stuff around a little bit. So basically, they're saying tangent of x is sine of x over cosine of x. And then we also have that x on the bottom, so it kind of looks like that. Does that make any sense? Okay, so tangent of x we just wrote like that. There's an x on the bottom, which we could just write as 1 over x. And then basically they flip-flop these to write it as sine of x over x times 1 over cosine of x. Why did they flip-flop them? So we can use that limit that we just learned. Does that make sense? So what's the limit as x approaches 0 of sine of x over x? 1. What's the limit as x approaches 0 of 1 over cosine of x? Think.
1.
Why 1?
Cosine 0.
Because the cosine of 0 is 1. And so we could actually do this part by direct substitution. Does that make sense? Can I just do the whole problem again? Is that what you said?
Yeah. Like, I just want to know, like, the tan of x, how do you get sine x over x?
Well, what's tangent?
Sine
So that's what we wrote, sine over cosine.
what is tan of?
But you also have this x on the bottom here. Right? This is sine over cosine. And then there's an x on the bottom, so we could just write that as 1 over x. We could have written this originally as tangent of x times. We could just split that apart like that. And then once we do that, that turns into that. Is that better? So especially as the trig functions are going, you kind of have to be a little creative sometimes. And you're looking for those limits that we just learned, that we just said we got to memorize. So sine of x over x is 1. 1 minus cosine of x over x is 0. And 1 plus 1 over
1
x.
plus x.
No, 1 plus x to the 1 over x equals e. And all of those are limits as x approaches 0. Okay, so here's the, as we go on, here's where you're going to run into trouble. Okay, that's too strong for this. You're going to have to be creative on some of these things. All right, I'm going to skip that one and I'm going to go. Where's it? That's what I want. So we're going to find the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Okay. How's direct substitution here?
No.
No dice, okay? And so there are a couple of thoughts that we might have, but they really don't get anywhere, okay? So when we start, what's in the top? What's in the numerator here? A true. Keep going. What else is up there? Binomial. We have a binomial in the numerator, correct?
Yes.
Now, we're going to use something that we have used in the past, but never in the numerator.
Rationalizing.
Yeah, we're going to use the conjugate. So we're going to multiply top and bottom by the conjugate of this thing. And this is a technique, this we will use fairly often. So if you get stuck on a limit, and there's a binomial, multiply by the conjugate. What is the conjugate of the top? The same two terms, change the sign. Okay? So what happens on the top?
Cancel.
We get x plus 1 minus 1, right? When we multiply conjugates, we square the first term. So the square of the square root of x plus 1 is just x plus 1 minus the square of the second term, which makes the top simply x, which is going to be a good thing. On the bottom, let's not mess. Yep.
How'd you get x again? You just foiled it.
Yeah, basically, except that we don't have to foil because the outside and the inside, since they're conjugates, the outside and the inside will cancel. So we just did first times first, which gave us that.
Yeah, I didn't know if you were just,
Yep.
if you just got x or if that's how you.
Yeah, it's once we foiled it, it came out like that. On the bottom, I'm not actually going to distribute. I'm just going to leave the x on the outside for now. God bless you. Why did I just leave the x there?
So you cancel out the x's.
So we can cancel out the x's. I know. So the x then takes out the x, which gives us 1 over square root of x plus 1 plus 1. And so, does that help us in terms of finding the limit?
Yes,
Why?
because you can substitute.
Because now we can use direct substitution. So the limit as x approaches 0 of 1 over the square root of x plus 1 is
1/2.
1/2. I was just going to say something. So, nothing's crazy hard, but the tough part is going to be deciding what to do. Which is why I would like you guys to spend some time today and tomorrow working together on your homework to help yourself get through some of the harder ones. Because I believe I'm done. I is. I is done.